Good morning, everyone. Thanks for attending our seminar number 2. If you're back by encore missing it the first time, welcome. If you're watching it for the second time, great. We made it even bigger and better. The part we added was some of the questions that were asked last time, some good questions. We'll cover those at the end too. So today, common vibration test snafus and how to fix them. My name is John Van Baren. Founder of Vibration Research 22 years ago, so I've seen a lot of stuff. We're going to cover the top 5, and then I have some fun stories from the trenches that I'm sure you'll find interesting, maybe even entertaining. I'm going to try to stick to the teleprompter. That's what they tell me. I have to say what's on the teleprompter, but I might stray from the written dialogue occasionally just for fun. Couple house cleaning comments. We have approximately, well, not quite 400 people because it's an overflow crowd today that couldn't make it last time. I fear that we won't be able to tackle all of your questions, but do feel free to type the questions in the chat area. We'll cover as many as we can today. If we don't get to all of them, we'll email out the answers to all questions by next week. And Rachel, my assistant here, who has put this webinar together, thank you very much. I'm assuming these questions would be available for everyone to see. You can probably email them out to the attendees too. There are some great questions. We're recording this webinar. We'll distribute it via email within the next week should you have an interest. And lastly, our marketing department will be conducting a short poll following the survey to ask about your top vibration testing challenges and snafus. Please take a moment to take the poll, and again, we'll distribute the results to everyone who participates. So let's get started. Top 5 snafus and solution. Number 5, noise floor issues. So sometimes you'll have a situation like this. You'll wake up your amplifier, your shaker, and you'll look at your controller and you'll see there's this great big spike right here. In this case at 60 cycles. If you're using 50 hertz power internationally, it will be at 50 hertz. Well, that's a power line noise. And the question is it going to affect my test? Well, if you look at the screen on the right, if your test line is right here where you want to test, there's nothing the controller can do to reduce this piece right here. So you're going to have that noise spike sticking into your test, and of course it's going to show up in your reports, and it's going to just be there. So what we want to do is get rid of that. What I like to do first of all is when I see that spike, I'll put my hand on the shaker. Just the tips of your fingers are very, very sensitive, and if it's 60 cycle noise, you'll be able to feel it. If it's actually present 60 cycle noise, you'll feel it. Now that tells you that your product has actually experienced that 60 cycle noise. Now if you don't feel it, either your fingers are not sensitive enough, or more probably it's actually electrical ground loop noise that's kind of a phantom signal. The controller thinks it's there because it's seeing something that it thinks is from the accelerometer, but it's really noise and it's actually not present. You can usually separate the two, and that'll give you some clues as to how to fix the test also. So to reduce the noise floor, you could choose a different shaker system for this particular test. I make that comment because a lot of times people buy the biggest shaker they'll ever need for any test. And if they're testing a big heavy item, and the first thing they want to do is test something that weighs less than a pound, well, bigger systems generally have a little bit of residual noise in the background. It's difficult to get rid of all of it. So perhaps the shaker is actually too big. So that comment. But generally that's not a problem. What you really want to do is go and eliminate the ground loops. Take a look at where and how the grounds are connected. Recognize that your amplifier has a ground tied in probably through the three-phase mains that are running the system, and that your controller has a ground also tied in to 120 volt or a 240 volt plug with a ground pin on it. Those grounds probably go to different places in your building, and it's to your best. If you want to get rid of all of that noise, the best thing to do is power them from the same raw power source. That might mean finding a tap inside your amplifier console to power the controller from. That may eliminate much of the problem right there. The other interesting thing to point out is the computer, of course, is going to be plugged in somewhere, and the controller instrumentation is going to be plugged in somewhere. The cool thing about Ethernet connection is on the 9500 we actually have a transformer inside, so there's no common ground between the Ethernet tied to the computer and the instrument. They have to have their own grounds, which means you can actually separate them. We have many sources of information also on Vibration Research University. Take a look at the Vibration Research University under the Experiments and Papers resource column and search for ground and noise. I think I found about 100 articles written about them, and those can be very interesting and educational. Number 4, accelerometer sensitivity issues. That's a common question. What accelerometer should I use? The problem with the sensitivity issue may be that the accelerometer sensitivities are incorrectly entered. I have seen it so often where the technician will pick up a box that the Accel was in and say, well, that's a 10 millivolt per G Accel, and you key it in and you find out, boy, that's just not adding up. Something's not right there, and careful examination reveals that the serial number stamped on the Accel doesn't match the serial number of the label on the box. Someone switched them and you entered the incorrect condition. Use system check and a displacement wedge to find out what it really is. And I'm going to come up to displacement wedge in a moment and explain it. The other thing that's a problem is the accelerometer is not powered or properly conditioned, or the wrong accelerometer is used for the test. Very common, people will use 100 millivolt per G Accel, not realizing that if they're using it to monitor something, it's going to have a resonance in it and probably has 100, 200, 300 Gs. Well, it's going to saturate. It's probably only good for maybe 50 or 75 or 100 Gs max. So here's how you can solve your accelerometer sensitivity issues. First of all, use a TEDS, that stands for Transducer Electronic Data Sheet, TEDS Accel. The software will go out and recognize that it's a TEDS Accel, and it will read before every test what Accel is out there. Make sure that the TEDS Accel that's connected at the end of the cable matches what's in the calibration system. Double check the input information in the system configuration. Make sure that that's all correct. Look for a green ring if a constant current accelerometer is used. We have green rings around our BNC connectors on the controller, and if it's green, that means that it's biased and the conditioning is working correctly. And then, of course, all you have to worry about is the millivolt per G correct. I mentioned the displacement wedge. Again, search Vibration Research University. There's videos and explanations of how it works. Notice that the red arrow is pointing to a displacement wedge. And that displacement wedge, you can visually see with your eye how much displacement is on the shaker. So it's another source of information, and you can go to typically about 20 hertz and put in 1/10 of an inch. If the controller says, okay, I'm happy and I think this is 1/10 of an inch, look at the displacement wedge and verify that it really is 1/10 of an inch. Another source of actual information that can convince you that yes, everything is good. I mentioned system check. when you run system check, what you want to see is that your accelerometer traces are all lying on top of each other. What you'll do is put a sine wave of a particular amplitude on the system, and whatever accels are hooked up should all track right on top of each other. If they don't, it's calibration differences somewhere. Another thing that can happen is an accel might be mounted upside down. Perhaps you have it mounted underneath a fixture oriented with the axis that it's measuring opposite of the other accelerometers, which usually isn't a big deal, except of course in shock testing. In that case, you'll want to invert the signal, and you can do that in the software just by going to the advanced input configuration page and clicking on the invert box. Then all the traces will lie on top of each other. All the phases should match exactly. Top snafu number 3, cabling issues. The problem with cables are always a problem, always a problem, because they're small, they're fragile, they're firm but fragile, and you have to be careful how you put them on, how you tighten them up. Make sure that the glue that you use to mount your accelerometer to the table isn't getting into the connector for your cable. That will cause problems, and you'll have intermittent connections. What I like to do is look at the time domain display on your controller. And if you see a nice clean signal, probably your cable is attached correctly. But if you see occasional spiking, just a big transient coming out, that's likely caused by a cable that's opening and closing just intermittently. And if you think about it, the way the constant current bias accelerometers work is they supply power with a DC offset. And the electronics which run the accelerometer and which may also supply power for the TEDS chip inside there, that cable provides it through that DC offset. Well, if the cable opens and closes, that's going to be a transient that comes right through the capacitor, and your controller is going to see it as a spike. It doesn't know whether it's a big G spike, like you dropped the accel or had an impact event, or if the cable intermittently opened. So if the shaker is sitting there very innocently looking or running some small acceleration, but you see a big spike on it, check your cables. It can also be caused by bad connection with a constant current sensor. Went into that description already. Or it can be caused by noise from cable whip. So the solution to these problems is, first of all, tape down your cables. They can be fragile. You don't want them whipping around and potentially breaking connections. There's a couple of red circles that you can see on your screen, and the red circles are just showing where the accelerometer cable has tape on it to restrain the cable from flopping around too much. So check out, and when you're running it, make sure you don't see your cables moving violently around. Number 2, top snafu issue number 2 is accelerometer mounting issues. You can see accelerometers, the sensory devices, are very important. First of all, recognize that a single axis accelerometer measures acceleration only in one axis. And what you want to do is make sure that the orientation of the vibration is in the correct motion. Here's a slip table with an accelerometer on the slip table, and if your accelerometer is mounted right here, as you can see, it might have been on this particular test where my mouse is pointing, well, it's not going to be measuring the correct motion. You can see where there's an accelerometer on the end of the slip plate, properly mounted to measure acceleration in this direction. So, of course, you can't mount your accelerometer measuring this axis when you expect it to be measuring that axis. This is actually cross-axis, and your accelerometer can measure some cross-axis motion even though it's not supposed to, and your table will generate cross-axis motion. So you might be fooled into think it's sort of working. seems a little noisy, but the table sure is running much harder than I expected. Well, check the orientation of your accelerometer. Accelerometers almost always have an arrow on them indicating what axis they're going to measure vibration in. And of course you can buy tri-axis, 3-axis accelerometers which monitor and give you readings on X, Y, and Z. And of course another problem is that the glue or stud is not holding it properly, or should I say wax is used to hold it down. So the solution to these problems would be mount it in the correct axis as mentioned, and use glue with a mounting base or a stud. A stud is always the best way to mount an Accel because it will mechanically tie it directly to the system. But super glue works really well also. It makes a connection that is either working or it's not working, so it's not really an in-between thing. If you use wax, and it's a common technique, don't use it on a control Accel, but you know, if you're using it for a monitor Accel, recognize that the Accel might fall off. Use tape on the cable so that if it does fall off, you don't damage it. And by dropping it on the floor, always a disaster for an accelerometer. You can crack the element inside, not knowing it, and get bad responses only at certain frequencies. So mount it in the correct axis. Use a glue or a stud when you're mounting your accelerometer. Lastly, and probably most importantly, is amplifier issues. Problem could be that the gain is cranked up. I'm going to come back to that one because there's a very good question asked at the last session about where the gain should be set. More probably, if you can't get anything to work, maybe the gain is turned off, turned down, or the amplifier is turned off. Or perhaps your amplifier had tripped and you didn't realize it, so you can't get anything out of the system. The Vibration View software has a number of very clever and powerful ways of checking the loop. You can have a system gain, and it's got to be within a certain section of gain reliable value in order to call it good, and so it monitors these things for you in the background. Solution to the amplifier issue is turn down the gain during the test start setup. Okay, that's always important. Sometimes that's forgotten. I violate that once in a while, and I got to slap my hand and say, John, if the amplifier doesn't need to produce anything, turn the gain down at least so that if something happens, a cable gets tripped on, a transient doesn't come out of the amplifier, drive the shaker to a stop or worse. So turn the amplifier up only when you're ready to use it and set it up to a predetermined gain. Typically the gain is just 100%. And let me just digress and go to that question right now. You'll see it come up later, but this is the appropriate time to talk about it. One of the questions was, one of the comments made last time was, we always turn the gain to 100%. Am I using up my amplifier or wearing out my shaker unnecessarily? The answer is no. That doesn't actually happen. The gain on your amplifier works with the gain stages in the controller to produce power going out to your shaker. And in the end, that power has to be controlled somehow, some way. The gain on the controller is very, very, very low noise. From our experience, it's about the lowest noise source made on Earth. We took great pains to make it as quiet as possible. The gain on your amplifier might not be quite as good of a quality. So if you have noise coming out of your system, we started with the 60 cycle noise peak, you might note to yourself whether that noise peak exists when the gain is turned all the way off. And if it's not there when the gain is off, but it shows up when the gain is on, well, that tells you something about noise, and it's probably 60 cycle stuff getting onto your shaker because of the amplifier and the shaker configuration. And then if you ran the gain at 50% and you still had plenty of gain left on your controller to get to 50%, and the controller will tell you if it runs out of gain on the controller side. It'll inform you, so you can run that gain at a lower position. It doesn't do anything to make your amplifier last longer or anything like that, but it may help solve the noise problem. Here's something if you're a musician or you've worked with other amplifiers. This is one thing I noticed is we have a keyboard piano, and there's a gain knob on the keyboard piano. That would be like the gain knob of the controller. Now, you plug that keyboard into an external amplifier, and if you buy the really low-cost external amplifiers, you know, the speakers on the tripods because you want to boom and make a lot of noise, well, if they're cheap, they have a lot of background noise, and you can tell right away. You turn the gain up, and you can just hear the hiss coming out of the speakers, you know, just shh there all the time, background noise. Well, it's very objectionable. So the solution is to get the best situation out of the pieces that you have, turn the gain of the piano all the way up and just use enough gain on the amplifier to get the volume required. That will give you the best signal to noise ratio for the system. And you kind of have the same situation with a power amplifier. They're made to be big and powerful, and perhaps the gain is going to introduce more noise in the background if it's cranked up higher. So that is the only reason why you would keep the gain at less than 100%. Well, I guess safety reasons too, it would limit the shaker output to some extent. So again, use the gain as needed, but it's not going to wear out your amplifier or anything like that. Here's a question. Let's see. Most vibrations tests are supposed to be done at frequency of resonance. What can we verify that we are running at the actual frequency of resonance? Okay, that's a good point. And let me just make this statement. Why do products fail? Well, they fail because you found a resonance somewhere. That's true probably 99% of the time. It fails because something in your product breaks into resonance. Take a capacitor soldered onto a circuit board, a transformer mounted into your chassis. Everything that acts like a spring mass damper system, even the little teeny IC chips that are located on a circuit board, they may have resonant frequencies, typically up in the kilohertz, very high, but they can resonate. Circuit boards will resonate, usually at quite low frequencies. And when they resonate, that is when you have failures. So the question is, how do you know where the resonances are? Well, a couple ways. Very good question, a couple ways. Number one, you can hear them. If you're running a test and the controller draws a really nice line and it says everything is running good, but you're listening to it, you should hear just a nice whoop, kind of a smooth sound like that. But when it gets up to higher frequencies, if you start to hear yoing, 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 it's something is resonating. And this is where controllers will have difficulty controlling because they're busy trying to keep that line nice and straight, and there's something in there that's banging, that's breaking into resonance and feeding back into the rest of the system, and you hear it because it's moving air molecules and it comes to your ears. Another way, when you hear it, the question might be, where is that coming from? And of course, the engineering way as well, let's put accelerometers all over it and let's find out where it's coming from, and that is a good way to do it. But another quick way to do it is use your fingertips. They're actually very good sensors. And I implore you to wear earplugs because I've done this for years, not probably with the hearing protection I should have, and sometimes these resonances get very, very loud. So when a test is sweeping and it hits a resonance, hold it on the resonance, walk up to it with your fingers, and you can usually find a spar or a rib. Probably, usually the most common problem is head expanders. You're going to find one that by just the touch of the finger, you can feel that it's resonating like crazy. Not good. And that, of course, is going to affect your test. So you want to get as many of the resonances out as possible, recognizing that, hey, things are going to resonate, but if they're, not too violent, you can usually accept them as they are. But that's a good question. That's how you can tell where the resonances are. Now, how do you do it for the test? Well, typically, you're going to put accelerometers on your product. Your test description should tell you where to put the accels. You're going to do the sweep. You're going to do a transfer function, and you're going to see what the transmissibility is, and the resonance will be located right at a particular spot. We can do a whole nother seminar on dwelling on resonances. There's a bunch of things that you have to pay attention to. When you sweep up, when you sweep down, and when you hold, the controller is going to indicate different frequencies for each one. The truth is you need to sit right smack on it and look at the phase and the amplitude, and then you can find the true actual resonance. But, in the end, you're going to have an accelerometer on it, and the thing is going to respond. And even if the item that you have the accel mounted to isn't actually resonating, something else might resonate and feed into that spot, and you'll still see it. Okay, another question. We're up to true stories from the trenches, but let me handle these questions quickly here too. Can you describe how to run a quick vibration survey on a test fixture to ensure there are no problems with it and or the accelerometers are mounted in the proper locations? Wow, good question, and there's actually lots of sub-questions in there. If typically when people are setting up a test, they're probably first doing a sign test, and everyone focuses on the sign test and does a sweep and hopes that it works. What you can do is just run a low-level random test on it, and the Vibration View software actually has ways to do that with low-level startup, where you can just get transfer functions of all your accelerometers and get an indication of what's going to happen. It will even tell you what is the highest G calculated to come out of that accelerometer. And you can look at that and, as I said, make sure that the cables are all working properly, you don't see the big spikes, and that everyone is happy. So a random background low-level check is a good way to ensure that things are good before you simply push the run button and say, okay, let's go for broke. And on a sign test, the first time you hook it up, I would certainly run it probably at 10% of level just to see how it's responding and what's going on, rather than pedal to the metal, go for broke right off the bat. Try to get a feel for where the resonances are and what you expect them to be. And there are some really cool tools that can be used to help you do this survey and find it out. Speaking of surveys, I can digress on one other issue. We invented a really interesting tool that works well with random. It's called Hideoff. And you can get a sine smooth like line almost instantly with a random test, and it will immediately show you where all the resonances are. Even if there's little teeny resonances, they're going to show up. So check back, and we can talk about that if you're interested. Okay, some fun stories from the trenches. This is where maybe I get to go off script just a little bit. Favorite saying of mine, a test should be implemented like a street lamp. What's a street lamp for? It's to provide illumination. Don't use your test like a drunkard uses a street lamp to provide support. Okay, what do I mean by that? Well, before you run your test, ask yourself, be honest now, why am I running this test? The number one answer is usually the answer that's given. The project is way behind schedule. It's on my checklist. I need to pass this test. So everything is done in your power as the test technician to pass the test. When really, you should ask yourself number two, I need to certify product survival and prove that this product exceeds expectations. That is why you really should be running a test. So solution number one usually overrules because, well, things are what they are. So here I actually saw this. I kid you not, I saw it. A controller was looped on itself with a T configuration, and the operator said, I just need to run the test and I just need to produce the report. Here is what he actually did. I have to say it was clever, but it's not right. What he did, this operator, management told him, we got to get this test run. You need to produce the test report. Stay late, stay tonight, do what you got to do. We got to ship this product. So what he did is he put a T in the drive signal, and he took the drive signal and he fed it back to channel 1. And of course the controller is going to control on channel 1, so it's going to produce, this was a random test, it's going to produce a random signal which matches exactly the profile from the drive. The controller can control a piece of coax very well, and it puts it on channel 1, and that's what we call looped on itself. The controller was looped on itself. Well, of course, you would understand that if the product isn't seeing any vibration, that's not fair. You got to turn your amplifier on, correct? So what do you do with it? Well, what you do is you feed that signal into your amplifier, and again, don't do this at home or in your lab. It's lying. What this clever person did is they fed it into their amplifier, and knowing that they needed to have 6 Gs of vibration on the product, they did put an accelerometer on the product, put that into channel 2. And then what they realized is if I set the gain of my amplifier to pick a number, 37%, I know that this amplifier, when I have the gain at 37%, produces 6 Gs RMS on the accelerometer mounted on the product, and it shows 6 Gs RMS coming into the input. And I had to chuckle when I saw this. You know, of course, that the product is getting nothing as you expect it is. And the argument was, well, no, it's 6 Gs on the product, and it's 6 Gs. It's like, this is the only way I can get it to control. My next challenge question was, well, you're running the test, and you're running a 15-minute test on this product. You actually only had the amplifier running for probably 12 of those 15 minutes. And there's the answer for that was, well, I really run the test for about 20 minutes just to make sure I had an acceptable amount of vibration time on the product. So that will give you the print that you want, put it in the file, but it's the wrong way to do it. And you can rest assured that solution number 2, verifying the strength of your product, was not accomplished. Don't do it. Here's another fun story. Customer called up and was doing a sine sweep test to 500 hertz. And they called up and they said, we've been running this sine sweep test to 500 hertz for years. And today we had to run it again. We hooked everything up. It doesn't work. It trips out at about 80 hertz. Why is it tripping out? So, you know, we talked about, well, how's your Excel mounted? Where is it? Do you got a product on it? What's your fixture look? The usual resonance troubleshooting problems. Finally, I asked, what kind of shaker are you running this test on? Oh, they said, it's a hydraulic shaker. Really? I said, a hydraulic shaker? How big is the head on it? Oh, it's a 6-foot head. And I'm thinking to myself, there is no way a hydraulic shaker typically can control to 500 hertz. It just can't be done. So, you know, I'm telling this to the customer, and the customer, of course, says, no, we have run this before. So I'm scratching my head, how could they have run it and convinced themselves that you were running it? Finally, a thought occurred to me. I said, turn off the tracking filters. Go in the software to this place right here. You can turn the tracking filters on and off. By default, we turn them on, but perhaps someone had turned them off. So that's all I told the customer. They went back, called me back a half hour later. Thank you so much. Yes, that was the problem. You solved it. We now can run our 500 hertz test. Everybody is happy. So I explained to the customer, well, you understand that with the tracking filters turned off, you're just measuring noise and assuming that that is the energy at that frequency, and it's not true. You are not testing it to 500 hertz. Well, doesn't matter. I got my report, and that's what went in the file. So I implore you, if you really want to test your product, you should never turn the tracking filters off on a signed test. Never, ever. Here's another story from the trenches. We actually invented this technique called Hideoff, instant degrees of freedom, because there's some tests out there that require high levels of random vibration. And the quality department wants to see when you're running a test that everything always stays inside the lines. Everyone has to be happy that it's inside the lines. And there are actually some tests that say if it ever goes outside the lines, that it's a failure and you cannot accept it. So the quality people are looking at this very carefully and say, well, this is outside the line right here. We cannot accept that. And we actually had a situation in aerospace. There's a high-level test that's run, and it's a very short duration to simulate a rocket launch. And other controllers drew this very smooth line when a step change occurred. Well, that's impossible. It can't be done. And what's happening is they're recycling some of the old data, and if they step the level up 10 times, they recognize, hey, we need to draw a smooth line. So take all the old data, multiply it by 10, and say that's what it is. And that cannot be done. If it is, it's in fact dangerous, because whenever you do a level change on a mechanical system, if there's a resonance in it, and that's of course what's going to break things, if there's a resonance in it, the resonance will shift. Maybe slightly, maybe a tenth of a hertz, maybe a half a hertz, but it likely will shift. And the problem is, if you use that recycling old data technique to give you smooth lines, you're actually going to be over and under testing at the location of the resonance, and worse, you'll never know it. So Hideoff is a way to predict exactly what the line is going to look like in the future based on what's happening. You can only do it on a controller. An analyzer cannot do this. And since we just came through a very interesting election cycle, I can tell you that it works this way. What we do is, since we're the controller and we're telling the shaker what to do, it's analogous to giving everyone a ballot and telling them, we've marked the ballot for you. You're going to go into the voting booth and you're going to deposit the ballot. And then we tell everyone to go do that, and we look at the results coming out of the voting machine. And if the results coming out of the voting machine don't match what we put into it, we know that something different is going on. And that's the technique that Hideoff uses. We know what drive is going exactly, the drive going to the shaker with the phases and everything. If they don't match, then we know there's a problem or an issue. And we can predict with almost 100% certainty exactly what the system is going to look like, even though you don't have 5 minutes of data, what it looks like right now. So that was a cool story from the trenches and what's actually happening. And I got to tell you this, when Spacex launch failed in the middle of 2015, I read it with interest, and the reported failure was a strut that we believe failed was designed and a material certified to handle 10,000 pounds of force, but it failed at 2,000 pounds of force, a 5-fold difference. Well, the question I immediately asked myself is, could that strut have been broken while it was being tested on the shaker? If you had a resonance, if you tested that at a short, high-duration test using what I just described a slide ago, you may have had a resonance and you would be forcing it way over what you thought it was getting. Ironically, this particular test in the aerospace requires plus and minus 1.5 dB, a very tight tolerance. Everyone wants to see it stay inside there for the whole test. But if you use the step-up basis method, you're going to overtest and probably be overtesting, who knows, 3, 4, 5, 6 dB, not 1.5 dB. So who knows, maybe it broke on the shaker. Now, they actually, the rest of the story was, you can go to the website and look it up yourself. The rest of the story was they went to their inventory bins and they found that the grain of some of the struts was the wrong way, and that was what they blamed on it. But it was a fun story for me to tell, and I'm telling you, it can actually happen, and people don't realize it. Here is another one. This is this goes in the lie, cheat, and steal column. Oops, I'm off script. Here's what happened. A customer set the accelerometer to 10 millivolts per G. They did all of their testing. Testing was completed, reports were generated, and then someone went back, and the quality people probably did a thorough job, and they found out that when they keyed in a 10 millivolt per G accel, the accel that the serial number actually was to 100 millivolt per G accel. So what that meant is they ran all of their tests at 10% of the level. So this customer called with an innocent question. They wanted to know how we stored the data for our stored data. You know, it's a digital file that we encrypt just basically for storage purposes to compress the data. We sort of encrypt it and it's buried in there, and we have the key to what goes where. This customer wanted to know where we kept the millivolt per G settings so they could adjust them as necessary. Well, we told them, sorry, we don't give that information out. That's company confidential, but you don't need it because you can export it to a spreadsheet. Just right-click on that file, export every piece of information out of it, bring it to a spreadsheet, bring it into any signal processing software like LabVIEW, and you can analyze it all. No, that wasn't good enough either. Well, we said, if you got the sensitivity wrong, you can just go to the Word document and you can change it, add a 0 to the 10. And well, that would be cheating, and we can't do that. What they were really saying is they wanted to change it and it would be untraceable. And we said, no, sorry, we don't give that information out. And so they probably had to go rerun the test. I hope that's what they did. And you know, just to illustrate this is serious, ran into this also on the web. There is a company that makes products for the military, and they actually had a phantom vibe test. Everyone knew about it. They told the employees, here's how you run the phantom vibe test. And it was a method of basically copying the paperwork, never running the test. Bear in mind that they were paid to run the test, and they certified that they were running the test, but somehow they got found out not good. And that was it's a bad decision. And this poor person, I don't know what the outcome was, but there was a fine and looking at jail time. The count carried a maximum penalty of 5 years in prison and a $250,000 fine. When they found out about it, they went back and had to pull all the products that were phantom tested, pull them back and retest them. It cost the Department of Defense $299,094. I love rounding it to the $94. Surprised it didn't have cents in there too. But that was what it cost to do this phantom test. So the moral of the story is, and the FBI, of course, points this kind of stuff out to all of us, don't fake the test. Just, you don't want to do it. Here's another interesting one, barely on script. The Volkswagen, when I heard that Volkswagen emissions were being questioned, right away I immediately thought, you know, I can see exactly what's happening. They need to get the product into the U.S. There's some stringent emissions tests. We're on a tight schedule. We need to get it through. And perhaps the test was, all we had to do is check the box that we ran the test. Well, as it played out, some very clever engineers, just as clever as the guy with the T in the driveline, figured out that if the steering wheel didn't move, and I don't know exactly what it was. I heard at one point it was the steering wheel not moving. I heard in another source that it was the rear wheels not moving with just the front wheels moving, front wheel drive. They knew it was on a dyno and it was being tested. So we're going to run it in clean mode. And then when everything is being used in normal mode, the customer, of course, wants the horsepower, so we'll put it in horsepower mode. And off we go. And that was, you know, another way of getting around a test which should not be done. And here's another one. Most recently, the Samsung Note 7 battery disaster. Could it have happened because of lack of testing? Again, you need to know whether your product is going to survive certain things. And I will say this, given a failure, there's always a test which can be used to most rapidly find the failure. But you know, other tests probably will indicate the failure too. It just may take more time or more effort. But the bottom line is do due diligence when you're testing. So if there are flaws in your product, they are found out before it's a disaster. Use rule number 2, test it to illuminate. Couple quick questions from last week when we ran it. Question number 1 was, would a 10 millivolt per G Accel be appropriate for G values in a 0 to 10 G, or would 100 millivolt per G be more appropriate? And that's a good question. 0 to 10 G, certainly 100 millivolt is appropriate. But again, if you're running a sign test and you're monitoring resonances, you could have a resonance that is a 10-fold resonance. That'd be 100 Gs. You're going to run out of capacity with your 100 millivolt per G test. I like to say my favorite Accels are 10 millivolt per G Accels, because with today's electronics and ability to isolate noises, you don't need those higher millivolt per G Accels. You can use a 10 millivolt per G Accel, believe it or not, with tracking filters turned on to extract a tenth of a G signal out of the noise floor and run a controlled sine sweep. It's unbelievable what you can do even with a 10 millivolt per G Accel. But just remember, the higher millivolt per G, yes, they do give you a little bit more signal for the level you're running, which is maybe pulling it out of the noise floor, but you're running into, just make sure it doesn't saturate. Look at the top G that the Accel is capable of handling and make sure that you never achieved it. Random, it's important in random because you're going to get G levels without Kurtosion of 4 times, 5 times the level of your RMS. Don't forget that. And of course in sine, as I mentioned, you're going to have resonances. Question number 2, if noise floor is present, would 100 millivolt per G Accel be more immune to a noise floor than a 10 millivolt per G Accel? The answer is sort of yes. Of course, you want to get your signal out of the noise floor, and the noise floor is going to be the noise floor, and it is what it is. And if the noise floor is there because of the controller, which of course there's always a noise floor, 100 millivolt per G is going to be higher, and it's going to be able to extract it out. Typically, noise problems occur because of ground loops, and it's because of a spike or something like that. And in that case, 100 millivolt per G Accel is going to make no difference or give you no advantage over a 10 millivolt per G Accel. Again, when we talked about it, the noise floor, I mentioned turning the gain of your amplifier up and down. Put your hand on the shaker, carefully of course, and see if the gain of the amplifier generates any perceivable background noise. And if it does, you know, solve that problem first. Don't try to fix it by using Accels that have higher sensitivity, because the net gain will be about 0. Question number 3, when you heard test this unit under test to X Gs, would you assume that value is peak or peak to peak? Yeah, this is a fun question because when you first come into this industry, you recognize that it seems like things aren't as uniform as you thought they were. You remembered that whenever you measured voltage, it would be an RMS value, in that whenever, if you measure a 120 volt signal coming out of a power plug, you knew that it was square root of 2 times going positive and square root of 2 times going negative. And that would be the peak to peak voltage versus the RMS voltage. Well, when we're doing sign testing, we talk about peak voltage. So if you're doing a 10G sign test, that's 10G positive peak G and 10 G's negative peak G's, or 20 G's peak to peak. But we still call it a 10G sign test. Now, when we're running random, we talk about an RMS test. So sign is peak, random is RMS. Universally true in the wide world. But recognize when you're running random, you're going to have peaks, and most people don't pay that much attention to them. We brought it to the test industry with the awareness phase with Kurtosion, because Kurtosion pays attention and in fact introduces peaks to try to get them into the resonances of your product and cause failures that you may see in the real world. So when you're running random, you talk about RMS, but bear in mind the peaks are there. And again, you got to have an accelerometer capable of handling those peaks that are there. A whole seminar could also be given on sigma clipping. My platform is you should never sigma clip. It's said that you need the sigma clip to protect the amplifier. While there may be some truth to that, really clipping, you should look at it from the point of view of I want to test my product, I should have true random going out there. And true random is going to produce 4 sigma, 5 sigma peaks. And remember, when you're clipping the drive, not the G's. You can measure the peaks coming out of your system with the sigma clipping set to 3 on the drive. You're going to regularly see 4 times the G RMS coming out of your accelerometer. So anyway, random is G's RMS, it has peak. Sign is peak G's positive. And I got to mention one other slight deviation in sign that you have to understand. First of all, when you talk of displacement in sign, then suddenly it changes from peak to peak. So we talk about a 1-inch shaker. That means it'll produce a 1/2 inch displacement up and a 1/2 inch displacement down. So if we say we're running a 10G sign test and it's 1 inch, down at lower frequencies, you're going to hit the frequency where 10 G's produces 1 inch. Well, that's 10 G's only in the positive, but it's a 1/2 inch up and a 1/2 inch down. They talk that way because shakers are always rated in inches of displacement total up and down. So I think it's just a way to make sure you're not ordering up a test that you can't run on your shaker. One other comment about peak G's. It comes back to tracking filters. Sometimes customers want to look at distortion as a peak, and they'll point out that a distorted sine signal that's running, say, 100 G peak actually has this little finger sticking out that goes to 110. Why can't we use that? Well, it's not at 100 G's. It's noise in your system. It's distortion, and it's not true peak. And if you do that, you're not really getting 100 G sine. I can tell you that it's done, but it shouldn't be done. Question number 4. We always turn up the gain to 100% on our amps. Are we taking life out of our amps? The answer is no. Mentioned that earlier. It's a fun question. Only the gain setting can change if you want to control the noise. Otherwise, hey, crank it to 100%. It doesn't matter. Oh, hey, got that question in there twice. Question 6, could you please explain once again about clip-off function in case of higher acceleration? I think what this question is about is random, and when you test with random, you can set the sigma clipping, and some tests even specify, they say set it to 3. They specify setting it to 3, and when you do that, you are going to clip the drive when it hits 3 times the RMS of the drive. Well, that only matches and correlates to acceleration when it's a perfectly flat system, and there's never ever a perfectly flat system. So you're clipping to kind of protect the amplifier to make sure you don't get too high of a signal into the amplifier. Today's amplifiers usually have very good ways of protecting themselves, and you shouldn't have to clip your drive signal in order to protect the amplifier. Recognize that when you clip, you're introducing intentional distortion into the system. And if you're honest with yourself, you could look at frequencies outside of what you're running, and you'll see that the noise actually comes up significantly because that clipping generates high energy, out of band energy harmonics. And if you have a resonance in your product sitting out there at those higher frequencies, you could actually be stimulating them and causing things to happen that you didn't realize. So take a look at what's happening out of band, and you can do that with the vibration view control software also. Set your lines of resolution so you look out to 5 kilohertz, 10 kilohertz, see what's going on out there. Again, go to Vibration Research University. There's papers on this and videos on this showing you what actually happens. My philosophy and my soapbox is you should never need to Sigma clip, turn it off. Can you comment on the function of the tracking filter? When you're doing a sign test, what you want to do is test at a particular frequency. So let's say that you had a resonance in your system at 102 hertz. Well, if you didn't have a tracking filter turned on, or let's go to the example of the hydraulic shaker. In that case, it was an interesting situation that usually is not repeatable, but in this situation there was enough noise generated by the drive output of the controller. Even though the controller would be putting out, say, a 400 hertz signal, this would cause motion on the table which was controllable. That's the ironic part. Well, that energy on the table probably was at 50 hertz, 100 hertz, something at low frequency. It was not, I assure you, at 400 hertz. So if you're running a test and your product has a 400 hertz resonance in it, and you sweep and you're controlling without a tracking filter, you think you hit it with 400 hertz, but you never did. So if your intent was to find resonances that may occur at 400 hertz, guess what? You never excited them. You're never going to break them with a test like that. So the idea of a tracking filter is it takes out all the extraneous distortion and artifacts that are present in your signal, and they're always there, hopefully low, but if they are there and they're being excited somehow, it removes them. So when you hit 400 hertz, you know you have 400 hertz of that energy, which guarantees a true test. So ending on a positive note, Vibration Research, our goal is to help you make testing easy, honest, and repeatable, and we all work towards that goal with our customers. And we have a great proven track record of reliability and support to get you where you have to go. And by the way, because of these snafus that I personally have run into in the field and our people have run into and reported back to us, they in the end need to run the test. Because of those situations, we've innovated these 4 things over the years. Field data replication, where we can actually repeat data from the field and make it happen on your shaker. Kurtosion was an example where the automotive industry said, hey, how come when we are collecting data in the field we see 150 G peaks, but when we take it and analyze it and put it on our shaker, we only see 30 G peaks. We see the product failing in the field, not on the shaker. How do we get those shocks back in? Well, we thought about it a long time, and we invented Kurtosion. Then customers, 2010, they want to know how much damage they're putting into their product. For years, they would say, okay, I need to run this test. The question is, how long do I run it, and can I accelerate the test by running it at a higher level? And the answer is yes, you can actually do that with the fatigue damage spectrum techniques of measurement. Again, Vibration University tells you a lot of stuff about it. And most recently, the Hideoff instant degrees of freedom. We're proud of that because it allows you to do an honest test on a step-up random test and get good results. And I can tell you that if you do a step up of your level, say from minus 20 dB to 0 dB on a random test, and the control signal looks beautiful and flat the whole time, it's recycling old data. It's the only way to do it unless you use Hideoff. And it's suspect, and it's going to be hiding stuff whether you know it or not. So we end on that note. Thanks a lot. If there's any additional questions or comments, I can answer them now or send an email. We'd be happy to answer them later if something comes up. And as mentioned, this was recorded. Thanks for participating. We'll send an email out with some summaries that we hope you find interesting, educational, and above all, helpful to your testing. So thanks again. Have a great day.